Zoom recording. Okay, so this section we're going to talk about it is in chapter 5. It's a new chapter. We're going to talk about a linear system of differential equations. So in general, it's... Oh, are we missing Anders, guys?
Oh, no. I'm here.
Oh, never mind. Thank you. So the section 5.1 is about first-order systems and applications. So we're going to look at first-order linear system, differential equation system, and some of the applications. One of the applications would come from the mechanic system of one mass spring. Let me try to move this over here. Okay. See. So you guys remember the graph of one mass spring system? Suppose I have a wall here, right? And this is the wall, here's the wall. And you can basically, there is a spring with a mass. Oops, what's going on here? So this is the mass. Recall this? And you can have an external function f of t pulling this mass, right? You guys with me?
Yeah.
Okay.
Yep.
So the spring has a constant k. And for the surface in the bottom, the floor may have the damping coefficient c. Right? So what's the differential equation that models what happens to this mass over here?
The m double prime of x.
X double prime. Yeah, here x is the displacement of the mass, right? Plus
k x prime.
k is about the spring. So spring
yeah.
is only related to the actual displacement. So kx.
The velocity, right? So it'd be the
something related to velocity, which is about the damping coefficient, right? So damping c times x prime. So mx double prime plus cx prime plus kx equals to the external force f of t. Recall this equation? Right? When c equals to 0, when there's damping free, then we only have mx double prime plus kx equals to f of t. That's when there's no damping. Okay. So this is only for one mass. Now we're going to look at a system with two mass. Okay. So here's this mass spring, and we have mass m1. Connect to another mass and m2. And suppose there's still an external force f of t dragging the mass m2. Is that good?
Mm-hmm.
Okay, now this is the spring number 1. This is spring number 2. Let's suppose the spring constant for the first one is K1. Spring constant for the second one is K2. Okay. And we're assuming a case when there's no damping at all. So damping coefficient C equals 0. And K1, K2 are the spring constants. So when the f of t is imposed onto m2, we can see that m1, m2 is going to be moving to the right, right? So the first will be stretched. So m1 would be moved to here. And then the second constant will be stretched as well. So m2 will be moved to here. You still have f of t after time t, right? You guys okay?
Mm-hmm.
Okay.
Yes.
Let's look at the displacement of m1. Okay, so m1 has been moved. The displacement will be x, okay? M2 has also been moved to the right, in this case now for Y. So X and Y are the two displacements of these two mass. X is for M1, Y is for M2. Good so far?
Yes.
All right.
Yep.
So we're going to try to write down two equations. Let me see, where am I at? We're going to write two equations. Two equations, one about the displacement of M1, one about the displacement of M2, okay? Which means one equation is about X and one equation is about Y, okay? Both X and Y are going to be the function of time, right? So X equals X of t, Y equals Y of t. Is that clear?
Yes.
Yeah.
Okay,
Yeah.
so let me move on. Let's keep going. First of all, let's look at mass M1. Okay, so here. So let's first look at M1 itself. M1 is connected basically to these two springs, right? So these two springs will give it the force, okay? It will be dragged by the spring number 2, trying to pull it to the right. It will also be dragged by spring number 1, trying to pull it to the left, right? So total force, F equals ma. Remember this from physics?
Yes.
All right, so total force. For this M1, there are two forces that's imposed to it. This is the first force, F1. This is the second force, F2, right? And our x-axis is towards the right. So this is the positive part, and to the left will be negative. So we should do F1 minus F2 equals to the mass, which is M1 for our M1. Acceleration, what is acceleration?
The velocity.
The second order derivative, right? Second order derivative of its displacement. So x double prime of t. Okay. Let's see what's going to be the F1. So F1. F1 basically is from the spring number 2, right? The spring number 2. So let's think about the spring number 2. Okay, the spring number 2 is here. This is the spring number 2. Can you guys see my mouse?
Yeah.
Okay, spring number 2. Spring number 2 has spring constant K2, right? K2. How much it has been stretched for the spring constant number 2? I mean the spring number 2.
Yeah.
All right, so Y is how much M2 has moved to the right, but at the same time, M1 has moved to the right for X. So what we have is it moved to the right from M2, which is Y, but at the same time, due to the movement of M1, we should subtract these X, okay, X of the movement from M1. That's going to be the total total length that the spring number 2 has been stretched. Make sense?
Yep.
Yeah.
Okay. So it's K2, open parentheses, y minus x, subtract F2. F2 is only about spring number 1, right? Spring number 1 has constant K1, and it has been stretched. Okay, it has been stretched completely only about M1, how much it has stretched, so just X. So that K1 times X equals M1X double prime. Okay, so this is the first equation about mass M1. We can call this equation 1. Is that clear?
Mm-hmm. Yeah.
Yep.
All right, let's move on to mass number 2. I'm trying to, let me see, can I move this one? Okay, let me zoom in a little bit. Let me stretch it to here. Okay, next let's look at mass M2. Okay, mass M2. Sorry, mass M2 is not directly connected to the wall, so we don't have to sketch the wall. Mass M2 is related to one spring and then one external force. This spring is actually spring number 2, right? So the M2 basically are under 2 forces. One is this right directionally F of t. One is the force that coming from the spring constant K2. Okay. So for M2, we have F total force equals MA again. Total force we have to the right, again, so positive direction, negative direction. To the right, we have F of t. To the left, we have this force comes from the spring number 2, right? Now, this force should be the same as the force that has been imposed on M1, okay, which is K2 times how much mass 2 has been moving and subtract how much mass 1 has been moving. So it's Ft minus K2, y minus x. That's the total force imposed on mass 2 equals to M2 times acceleration of the mass number 2, which is going to be, is it related to y or x, guys?
What do you mean exactly?
I mean,
the
what's going to be this acceleration when we're looking at M2, mass M2?
Would it be y, wouldn't be?
Yeah, it should be related to the displacement. This time it should be y, right? Second order derivative. Is that good?
Mm-hmm.
Okay, so this is equation number 2. Okay. So if we put those, let me see. So if we put those 2 equations together, we have a system of equations. One is about x, one is about y, and they're intertwined, right? For the x, we have m1 x double prime equals 2 k2 y minus x minus k1x. That's equation 1 that we just derived. Equation number 2 will be m2 y double prime equals f of t minus k2 y minus x. This is equation number 2. All right, so this is one example of system of equation. We've got how many equations?
2.
2 equations about x and y. What's the independent variable here?
T.
Time t, good. What's the dependent variable?
Displacement.
Displacement.
Yeah, displacement. So there are 2, so x and y, right? What's the order of the system?
First.
X and Y.
First or second order?
When you have squared.
Huh?
Second order.
When it's squared, the second order.
X double prime. So it's second order system, okay? Any questions so far? No response at all?
No, I guess no questions.
Okay, so this is just an introduction, okay, introduction of when you might be seeing these kind of system of equations, okay? In mass spring system, once you have 2 masses, then you would have 2 equations related to the 2 displacement. Okay. And because y and x appear in both of these two equations, so you have to look at them both to solve for x and y. So let's look at the in general. So in general, what does the second order system of equation look like? Okay. So we may looking at a second order. So you should have x double prime and y double prime, right? Second order, and you can put everything else to the right hand side. X double prime will be related to a function, y double prime will be related to a function. The function might be related to independent variable t, okay? Also, you would have x, y that appears in the function, and then first order, okay? Just any order that's lower than the highest order, right? For some functions of f and g, okay? What are the solutions? What are we solving in these kind of system equation, guys?
Would we have to involve the place?
When you see such differential equations, what are you trying to solve? Are you trying to solve t?
X of t?
Yes, you're solving for x
And y of t.
and y of t. So that's the general second order differential equation. The system of differential equations will look like that. Is everything good?
Yep.
Yep.
Yes, question. Is that Donovan?
Say that you mean, so x of t and y of t are the solutions for like f and g. So the functions f and g, the solutions are x of t and y of t.
Oh, yeah, this f and g are just in general, okay? It really depends on what you see. Let me give you some examples. Let's see. So in this case, right, in the first equation, we can write this as x double prime equals to this whole thing divided by m1. Right?
Okay, yeah.
Okay, let me see. Where's my pen? Okay, so that's, in this case, I can write this as x double prime equals the whole right-hand side divided by m1, right? So in this case, this whole thing will just be the g, okay, over here. So it's just a function of x, y. You might see t, you might see x prime, you might see y prime in the right-hand side. That's what they're talking about.
Okay.
Yep. Other questions? However, the keynote here is, even though you see such system of equation, what we are trying to solve is we're trying to solve x and y. So that's the introduction of second order system. In order to solve for second order or third order or fourth order, we need to first of all know how to solve first order system of ordinary differential equations. Okay, so let's first think about what will be the look of first order ODE. Okay. Any thoughts? Okay, now suppose we're looking at a first order system, okay? And there are n dependent variables, x1, x2. So we should have n equations, okay? Highest order is first, so x1 prime, x2 prime, x3 prime, and you to the last one, xn prime. Right? Independent variable is t. Okay, let me see. Independent variable is t. So each one of the function would be related to all of these variables, x1, x2, to x of n, and with variable t. x2 prime will be the same thing, be related to all of these variables. And you might see t in it too. X3 prime would be a function related to all of these dependent variable and independent variable t. And xn prime will just be f of n, x1, x2, x of n, and t. So this would be a first order. Let me see. Did I miss the system word? Where's my pen? Ooh, okay, so a first order system of ordinary differential equations, okay, of n dependent variables. So they look like this. This is the general look of it. If all of these functions are linear, okay, linear. You guys know what's linear?
No
The
squares and cubes.
Yeah, only raised to the first power, right? Then the system is called first order linear system. Okay, linear system. So let's look at one example here. Okay, this example one, you see there are two dependent variables, y1, y2. It tells you the independent variable here is x. Okay, this is a first order linear system because y1 is raised to the first, while y2 is also raised to the first. Okay. In this linear system, we're solving for y1 and y2, right? It also gives you the initial condition y1 at 0 is 1, y2 at 0 is 2. The equations, we can label them. This is equation 1, that's equation 2. Okay. All right, I'll give you guys a few minutes to think about any ideas you want to use to solve this system. Or is there a particular equation you would start with? Give you guys a few minutes to observe. Okay. Which equation might be easier to start with, to start solving with?
Well, the y prime first one.
First one, why, Eric?
Because you've only got one y variable. Y dependent variable.
Because the first one is only about a one variable, right? And we've done the equation like this before, so you can just start with the first one. Okay, first one doesn't have y2 involved. So,
Makes sense.
Solution, okay. y1 prime is y1, right? y1 prime is derivative of y1 with respect to dx, right? dy1 over dx equals y1. What can we do with this? Separable, yeah. Let's separate y1 and let's move the dx to the right, right? So we have dy1 over y1 equals dx.
Then take the integral.
All right, and then let's integral both sides. So we have 1 over y1 dy1 equals integral of dx. Is everybody good so far? What's the integration of the left-hand side?
Natural log of the absolute value of y1.
Natural log of the absolute value of y1 equals to the right-hand side, which is bx plus c, right?
Yeah.
Can we get the explicit solution?
Yeah, you got the exponential everything.
So let's raise both sides by e, right? So we'd have absolute value of y1 equals e to the x times e to the c, right? Which is c1 e to the x. Okay, so y1 basically is plus minus c1 e to the x, right? Can we just say y1 is some constant times e to the x? Right? This plus or minus c1 would just be a constant c2. Good?
Yeah.
Is there any way we can figure out this constant c2?
Initial condition.
Yeah, initial condition.
Yeah, so use initial condition for C2. We've got two initial conditions. We should be using the one that's related to y1, right? So we have y1 at 0 equals 1. So it tells us when x equals 0, y1 equals 1. Let's plug in. So we should have y1, which is 1, equals C2 e raised to the 0. E raised to 0. All right, do we get C2?
Mm-hmm.
C2 will just be 1, right? Any questions, folks?
No.
All right. Okay, so basically it tells us y1 is e to the x. So that's one solution for y1. You know how to do this, right? In chapter 1, we talked about separable equations. This is first order, so it's pretty straightforward. All right, so we've got y1. Next, think about y2, right? Y2. Any thoughts?
Can't we do? I forget what it's called, but where you have use the operator or something where you have e to the x equals like something with y2, because you have the y prime and then you have a regular y and then you have a function of x on the other end.
Linear? Are you talking about a linear first order linear differential equation?
Yeah.
Okay, let's see. Yeah, we might need to do that. But first of all, we understand y2 is being discussed in the second equation. Where's my pen? Okay, so this is where the y2 has been told you, right? So we should be using that equation. So y2 prime equals y1. Now it's already given, y1 minus y2. Yeah, so Eric, you can move the y2 to the left-hand side. So it's y2 prime plus y2 equals e to the x. Once we substitute the y1 in. Yeah, this is the linear differential equation, right?
Yeah.
This is the first order linear differential equation where you need to recognize the P and the Q. You guys remember the integrating factor? Yeah, so this is P. This is Q. Recall that?
Yes.
So the integrating factor will just be, R of x, right, equals e raised to the integral of
1.
P of x dx, yes, P of x dx, which is e raised to the integral of 1 dx, which is e to the x, right? Therefore, y2 equals to integral of,
Operate.
is it the rx qx dx divided by integral of rx dx? Okay. So we have an integral of e to the x dx on top of the integral of e to the x times q of x, which is e to the x dx, right? I think, am I right on here, guys?
I think the denominator is
R of X.
different.
I think the bottom is only RX.
Yeah, it's R of X.
Yeah, I thought it was just
I don't remember
R.
this.
There's no integration.
Yeah,
Yeah, this looks right. So there's no dx here. So I usually just go from the integration and then solve. I don't memorize the formula here. So that we integral of e raised to 2x dx. You guys have a very good memory. Okay, so integral of e to the 2x dx, right, on top. Good so far?
Mm-hmm.
Okay, so what's the integration of e to the 2x?
E to 2x divided by 2.
2x divided by 2 plus a constant c, right?
Mm-hmm.
The bottom is just e to the x. Okay, so what we have here is we can do this e raised to the 2x over 2 divided by e to the x. And do this divided by that, and plus c divided by this, right? The first division just be e to the 2x over 2 divided by e to the x. Second division will be c over e to the x. These two could be reduced, right? You can reduce e to the x. You just have e to the x over 2 plus c over e to the x. Good so far?
Yeah.
This is the general solution for y sub 2, right? We're almost done except for looking for the c. Okay, so use initial condition. Let's see what's the initial condition. Initial condition is y2 and y2 of 0 equals to 2. So y2 of 0 equals to 2 for this constant c, right? So that means my y sub 2, okay, would be 2 equals e to the 0 divided by 2 plus c over e to the 0. So 2 is 1/2 plus c over 1. So c will just be 2 minus 1/2, which is 3/2. And the y2 here will just be e to the x over 2 plus 3 over 2 over e to the x. Good so far?
Yes.
All right, so in the end, we can just put the two solutions together, right? So we have y1 and y2. Let's put them together as solution to the system. y1 is just e to the x. y2 is e to the x over 2 plus 3 over 2 e to the x. Any questions for this problem?
Is this kind of what you meant when they relate to one another? Like, since you end up using e to the x to find the y2?
Yeah, so first of all, for this linear system, it has two variables you need to solve for, y1, y2, okay? You can solve for the y1 basically by itself. You don't have to use y2. However, y2 depends on y1. So the idea is you first of all get y1 and then use y1 to solve for y2. And the second equation, based on its format, we understand this is a linear differential equation. Therefore, you can use our previous knowledge of integrating factor to solve for y2. Eric, does that answer your question?
Mm-hmm.
Okay. I mean, different systems are different. It all depends on what it looks. You can take different strategies, right? Sometimes one strategy might be easier than the other one. It really depends on what you're given for the system, okay? So that's one example of first order linear system. Let's look at example 2. Example 2 is also a first order linear system, okay, linear system. In this first order linear system, we have dependent variables are x and y. You guys can tell?
Yeah.
X and y are dependent. It tells you the independent variable is actually t, okay? So we're solving for x and y, and both of those are functions of t. The initial conditions are also provided. X, when t equals 0, the x value is 1. Y, when t equals 0, the value is 0. Okay. Now take a look at this system. It's different from our system number 1 that we just solved. System number 1, you can just take out one equation and solve it. But the system number 2, if you look at it, x and y, they are intertwined. You see x prime is 2y minus x, while y prime is equal to x, right? When you're thinking about our previous knowledge of solving system of equations, what methods we have in general previously when you have algebraic equations?
Can we substitute or put equation 2 in equation 1?
Yeah, you can do substitution method, right? Substitution method is one method we typically do a lot. You can also do like elimination method for a system equation. Okay. So let's try one method here. Apparently you guys are interested in substitution method. Substitution method, where's my pen? Okay, so let's call this equation 1. Let's call this equation 2. We're solving for x, solving for x as a function of t and y as a function of t. Now the equation 2 is relatively simple, right? Y prime equals x. Okay, so let's just plug equation 2 into equation 1. So substitution method. Okay, plug equation 2 into equation 1. Are you guys following me? Okay, so let's see. We have equation 1 is x prime, right? It says x is y prime. So we have y prime, its prime equals 2y minus x, which is y prime, right?
Right.
Okay, let's see. So that tells you y double prime equals 2y minus y prime. Let's call this equation 3. Equation 3 is only about y, which is good. Okay. So you just go ahead and focus on this equation 3 and solve for y. Once you got the y, you can solve for x.
We would just do the characteristic equation, right?
Yeah, let's first remove everything to the left-hand side. So we have y double prime plus y prime minus 2y equals 0, right? What's the name of this equation once you see right-hand side being 0?
Homogeneous.
Yeah, homogeneous equation. So we should do characteristic equation.
Isn't that r squared plus r
Yes.
minus 2?
Yes. We have r squared plus r minus 2 equals 0, right? Is this easy to solve?
Yes.
Factorization, right? We have r minus 2, you can factor it to 2 and a 1. We want to have plus r, so plus 2 minus 1, right? One solution is -2 and the other solution is +1. And both of these are real solutions, right? Both of them are real solutions. Okay, can you write down the solution, general solution for y?
Yeah, we just use the e dx's, right?
Yeah, I'm gonna do, so we have y's of t be c1 e raised to -2t plus c2 e raised to the t, right? General solution.
then use initial conditions?
Yeah, you can use initial condition, but the initial condition, let me see, where's my...
Oh, but you want to do anything here.
Initial condition here is actually related to both x and y. Think about if you use initial condition now, plug in 0. If you plug in 0, you still have C1 and a C2, right? You still have C1 and C2, two variables. For two unknowns, we need to have two equations. So let's see if we can get the other variable that we're solving. Can we get x?
Mm-hmm.
Okay. So
Can we just take y prime?
yes.
Or get rid of this?
Mm-hmm. Because equation 2. So by equation 2, your x will just be y prime, derivative of y. So just doing derivative of this part and derivative of that part, right? We would have negative 2 c1 e raised to negative 2t plus derivative of the second part, which is still c2 e to the t. This is also a general solution containing c1 and c2. Everything's good?
Mm-hmm.
Yeah.
Okay, so next, let's solve for c1 and c2 by using initial conditions, right? We have two coefficients to determine, so we need to use two initial conditions. One is x of 0 equals to 1. The other one is y of 0 equals to 0. Okay, so let's plug in 0 here and 0 there for x and y. So x of 0, okay, here's x. Let's plug in 0. I get negative 2c1 plus c2 equals to 1. Function y, you should be looking at this equation here, y. We're going to plug 0 in for the time t. So we have c1 plus c2, according to the initial condition that's being provided, equals to 0. Is that good, guys?
Mm-hmm.
Yes.
Good.
Let's call this equation 4, equation 5 for c1 and c2. This is pretty straightforward, right? Any method we can do?
Just substitution.
You can do substitution method, you can do elimination method. What's the matter? All right, I think over here, I would just go ahead and do elimination method. I would do 5 minus 4. Okay, equation 5 minus equation 4. Then I would be having c1 minus negative 2c1, which is 3c1 equals to negative 1, telling us c1 is negative 1/3, and therefore c2 will just be positive 1/3. Is that good?
Yeah.
All right, so once you plug C1 and C2 into the general solution, we have particular solution, right? So particular solution to the system will just be x of t equals to negative 2c1. So it's negative 2 times c1, so 2/3 e to the negative t plus c2 e to the t. Second unknown, y of t. Okay, y of t equals c1, which is negative 1/3 e to the negative 2t plus c2, 1/3 e to the t. That should be the solution to the system to this initial value problem. Any thoughts? Any questions?
Mhm.
Any comments? One question, Dr. Wu.
Yes.
Can we have non-homogeneous equation?
Oh, absolutely, sure. If it's non-homogeneous equation, what do you do with non-homogeneous equation?
Y sub C and Y sub P?
Yeah, correct.
Okay.
Use all your knowledges to solve it, right? Okay.
All right.
We've talked about how to solve one equation. The system of equation is just a combination of several equations together. Okay. Any other questions? Can we move on to next page?
Yeah.
Yeah.
Think so.
Okay, so great. Let's move on to next page. So next page is let's visualize. Okay, let's visualize the system equation into certain graphs. We understand previously, if you only have one first-order differential equations, you can look at its direction field, right? You guys recall direction fields?
Those are the same things like
Vector field, right? Mm-hmm. So you can where is it? Should be here. For example, if you have y1 prime equals y1, then you can construct a direction field and look at the solution curve based on the initial condition that is given. So same thing here. If you have a system of first-order differential equation, okay, we can get a field called phase plane. Okay, phase plane. The phase plane is basically generated based on the equation that you're given. For example, the equation tells you the derivative, okay, for the x position is 2y minus x. Derivative y, okay, on the y direction will just be x. So the phase field will just be full of those vectors that contains x prime and y prime. Okay. For example, at x equals 1, y equals 1, at that particular point, what's going to be the vector, okay, that would be on the phase plane? Let me copy the system down again so it'll be easier for us to see. Okay. So I'm going to write the system here. Okay. So we have x prime is 2y minus x. And y prime equals x. So the phase plane basically is a bunch of vectors, okay, that's based on x prime and y prime. Okay. All right, at x equals 1 and y equals 1, can we plug x and y in here for x prime and y prime?
Yeah.
The x prime
would be 0 and 1.
Second one would be 1. The first one would be x prime, which is 2y minus x. 2y, so 2 times 2.
Okay.
Sorry, 2 times 1 minus 1, right? So be 1.
Okay.
So that tells us on this phase plane, right? Phase plane, okay. Here's x, here's O, here's y. At 1, 1, so 1, 1. There should be a vector, okay, that's about these two derivatives. So the vector will be x prime, 1, comma, y prime, which is 1. Okay, so 1, 1. Make sense?
Yes.
And we can generate a bunch of vectors at different points, right? Different points. So eventually, that will give us a phase plane. Okay, phase plane. Now let me show you. From this website, you can generate a phase plane. Let's see, where's my phase plane? It's blocking here. Okay. Move this. Okay, so this is the website you can go to for phase plane. I entered x prime equals 2y minus x, and I entered y prime equals x. Okay. Let me delete this. Let me delete it. Great, let me redo this. Phase plane plotter. All right, so I entered 2y, so 2 times y minus x for x prime, and y prime is just x. And the next basically defines what's the minimum, maximum for the x value and a y value. Let's generate the phase plane. This is going to be the phase plane, okay? We did one example of when x equals 1, y equals 1, the vector should be pointing 1, 1, right? You guys recall?
Mm-hmm.
Okay, so this phase plane just talks about different vectors at different points. Now, for our particular solution to this initial value problem, we should indicate our initial condition, right? Initial condition. So the initial condition is when t equals 0, I have a point 1, 0. Okay, 1, 0. So let's just click that point. Let me see, where's my... So 1, 0. So 1, 0 is here. If you click, then this would be a curve that's talking about the solution. This is the solution curve. Okay. Any question?
Am I the only one who doesn't see any curves? And
Yeah, I don't see anything either.
I just see the example 2 paper and
Really?
Yeah, you have to like
that page.
reshare. After you click on the link, you have to reshare your screen.
Oh,
Yeah.
my bad. It says my screen sharing is paused. Huh, my bad. Okay, now can you see?
not yet.
The same thing on my end.
Nothing yet.
What? Resume share. Can you see anything?
Nope.
Nope.
No.
For our presentation, he had to. He had like switched over a different link, and he had to like unshare his screen and then pull up the other thing and then hit reshare.
Okay, let me stop share and then reshare. Okay. Stop share. Oh, there's chat. Okay. Let me reshare. Share my screen. Okay, share my screen.
Bingo.
Oh,
There it is.
Yeah, now it
Yeah,
works.
now we see it.
Great. Okay, so what I did is I went to this website and I entered x prime equals 2y minus x and y prime equals x. And then it gives me a bunch of these vectors. Okay. And then I entered my initial condition. The initial condition is the initial value of x and y. Let me see. So initial value of x and y is 1, 0, 1, 0. Then I just click the point 1, 0, which is here. If I click, then this curve will be generated. Okay, the curve again follows the flow of the vector, right? Can you guys see the curve?
Yeah.
Okay,
Works.
so this curve is the solution curve. Okay.
Do we ever need to change the min and max?
You don't have to. If you want to change it, you can change it. You can change it to -10, +10. Depends on the range of your x and y values.
Yeah.
Okay, yeah. But in this case, I think, in our case, -5 by default would be fine, right?
Yeah.
Okay. Now let me ask you one question to see if you have been thinking about it. Think about our solution. Okay. Our solution, we have x and equal to some t, y equal to some t. Okay. But why the graph is only one curve?
Because they're related to each other.
Yeah.
Great.
It's like the mass where one affects the other.
Yes, that is because our solution over here.
It's still independent variable t, so we're in
Okay, let me see. So this is a parametric equations, right?
Yes.
Parametric
Are you
equation.
trying to show something?
The parameter. Can you see my screen?
No.
We still see the curve.
So again, you don't see my screen again?
Mm-hmm.
You have to do the same thing where you unshare it and then share it.
What do
Yeah.
I do? Stop sharing. Let me unshare them. Okay. I'll be right with you. That's so weird. No, my screen. Okay. See the screen?
There
Yeah.
we go.
Okay. So I was talking about both x and y are expressed in terms of variable t, but the curve we have here is actually y equals to a function of x. Okay. The reason is, if you recall in calculus 3, okay, these two equations are parametric equations. The parameter here is t, right? So parameter is t. So basically it indicates y would be a certain function of x. Make sense? Guys? Okay. So if you eliminate the variable t, you can write this y as a function of x, and the graph will just be illustrated by using this curve. Okay. But anyway, this is just a solution curve to this initial value problem. Okay, well, please excuse me for a minute. I'm gonna mute myself. I need to go drink some water. You guys can chat with yourself. I'll be right back, okay.
I think my favorite part about all this is getting here early and watching all of you guys join with your cameras on for like 2 seconds and then immediately turn it off.
Yeah, that's the funniest thing.
It's random. Someone comes in to shut it off.
Can you hear me, guys?
Yes.
Nope.
All right, I'm back. So the last part of this section is we've seen some cases of solving first order differential equation in the system, okay? And a lot of times you can use different methods to solve it. With this in mind, we can transform those nth order differential equations, higher order differential equations, into a system of first order ODEs. Okay. Let's see this. Suppose I have a higher order differential equation with nth order, right? So then basically it looks like x to the nth order equals to a function that depends on all the lower order derivative x and the independent variable t. We would be able to transform this into a system of first order ODEs by doing some manipulation here. Let me get my pen back here. All right, so we can let x to be x1, x prime to be a variable x2, x double prime be x of 3, and then eventually the last derivative to be x of n. Okay. Then the equation of the system of first order ODEs would be, okay, we can just say x1 will just be x, right? x2 would be x prime. Oh, let me do this. Sorry. So x1 instead of that. Okay, let's see. My bad. I should be substituting this. Okay. So x prime, which is the first order, right? So what is x? X is x1 prime. So x1 prime will just be x2. And let's plug x2, which is x prime in. What do we say for the second equation? Guys, for x double prime, is that just x prime, it's prime?
Yeah.
Okay, what is x prime? X prime is x2, right? So this is just x2 prime. So the second equation will be x2 prime would be x3. Similarly, you can say x3 prime would be x4, right? All of these are first order differential equations about the variable x1, x2, x3. And then once we got to here, what do we say? We got xn minus 1 prime equals x of n. Is that good so far?
Good. I don't know. I guess.
Do the first three equations make sense to you?
Yes.
Yeah.
Okay. And based on this pattern, you can get this equation right here, right?
Yeah.
Okay. Now these are about x1, x2, x3 up to x of n minus 1. But we have the last new variable we generated, which is x of n. So let's see. X of n, its derivative. Okay, so xn, its derivative. Let me pull this down. Would it be x to the nth order, n minus 1th order derivative? Take one more derivative, which is x raised to the, is that nth order derivative?
Mm-hmm.
Right? Now, based on the original equation, x to the nth order derivative would just be f, where's my dot? Okay, it would be f of x, which is x1, x prime, which is x2, and keep going up to x of n, comma, t. So the last equation will just be f of x1, comma, x2, up to x of n, comma, t. So this whole system, okay, this whole system would be equivalent to the original higher order differential equation. So you change one equation into a system. Okay. Why do we need to do this? Because a lot of times first order differential equation will be much easier to solve because the order is only first. Okay. Let us fill in the blank. This is a system of how many equations?
N equations.
N equations of
N unknowns.
N unknowns. Yes, N equations of N unknowns. Okay, we have a few minutes left. Let's do example 3. Okay. And I think we'll be done once we finish example 3. And there are 2 more questions, we can leave it to next time. So example 3, transform this ordinary differential equation into an equivalent system of first order ODEs. What is the higher order derivative? The highest is 4th order derivative, right?
Yes.
So we should have x1, x2, x3, x4 to be generated. Okay. And we're going to just let x1 to be the x, x2 to be x prime, x3 to be x double prime, x4 to be x triple prime. Is that good so far?
Yes.
All right, next let's try to get the system of first order differential equations. Remember, each one would be first order, so we should have x1 prime equals something, x2 prime equals something, x3 prime equals something. Okay. Okay, let's see. What is x1 prime? Let's look at what we have here, guys. x1 prime equals x prime, which is what?
Negative. Oh, what is just?
X2?
Yeah, it's just x2. You guys see that? x1 prime equals x prime equals x2, right? What's x2 prime? x2 prime will be x double prime, which is x3. Okay, x3 prime. x3 prime would be x triple prime, which is
X4.
x of 4. These are the first three equations. Lastly, we have x4 prime, right? Okay, so let's see. x4 prime would be x to the fourth order derivative, right?
Which is equal to everything from the top.
Which comes from this equation, right? This is where it talks about x to the fourth order derivative. The x to the fourth order derivative equals to cosine 3t and subtract 6 x double prime. What's x double prime? That's x of 3 plus 3 times x prime, which is x of 2 and a minus the lastly, which is x. Okay, minus in the end, it's minus x, right? So minus x, which is x1. Is everything good?
Mm-hmm.
So that's how we transform this fourth order differential equation into a system of 4 first order ODEs. Okay, let's stop right here, guys. I will upload this video onto YouTube in case you have any questions. Okay?
All right.
Thank you.
No
Thank you,
problem.
Dr. Wu.